Hi, I'd like to thank the organizers for the opportunity to talk to you about the nuclear star cluster. So this work is done in conjunction with a whole bunch of folks here. So the two things I'm most interested in terms of the Milky Way nuclear star cluster is the physical properties, its formation, and the evolution of the cluster. So the physical properties and how it got there. And then two, the interaction between a stellar cluster and a supermassive black hole. To begin, though, let's look at the bulk properties of the cluster, what we know about it today. So in the background, the image is an HST near-infrared image. So the half-light radius is about 2.4 parsecs. Reiner did a lot of this work. It doesn't look like this half-light radius because the extinction is extremely high in the galactic center. You can tell like there's all these bands of extinction, but I promise if you take away the extinction, that is where the half-light radius is about. The total mass is about 10 to the 7 solar masses. It's about 5 to 10 gigayear-old. In the inner 1 parsec or so, the stellar density is very high. It has the age comes from, I was the one who got this age. The person who got the age is right there. The age comes from modeling the isochrones of the red giants, essentially. Okay. So the inner central parsec has basically 1 million solar masses per cubic centimeter. So this is basically the most dense region in the Milky Way. In the very, very center, that's what we talked about yesterday, is the young stellar cluster. And that's about 1 to 4 times 10 to the 4 solar masses. And that's about 4 to 6 million years old. OK, so that's kind of the bulk properties. But what I'm going to concentrate on is to go even closer with adaptive optics. So this is an adaptive optics image taken at Keck. You can tell this is Sagittarius star in between these 2 points. What adaptive optics, and especially spectroscopy, lets you do is to separate out the different populations at the galactic center. So like I said previously, there are both an old population and a young population. So with spectroscopy, you can separate out these 2 types. With colors alone, it's really difficult because this H minus K color is very small, and the extinction is very large and has very large variations. OK, so how does this work? This is an image of an integral field spectrograph called OSIRIS. Basically, every pixel location, you get a spectrum. And so here, for example, this is a spectrum of SO2, which you know and love. And it's a young star, whereas this star, it's an evolved red giant. You can tell it's young because it has strong hydrogen absorption lines and basically no other lines. You can tell these are cool stars because of all the metal lines that are in there. So this allows us to separate out the populations. And at the galactic center, of course, we don't just have spectroscopy. We do a lot of proper motion work. And these are now color-coded by the type of star. So the old stars are in red. The blue stars are young. And then the proper motion vectors are these little arrows. So even if you didn't really know what the black hole was, you could sort of tell because the proper motion vectors go crazy here. Right? So it also tells you in this image that young stars are very centrally concentrated around the black hole, which is weird. We don't have, so we have also the line of sight velocities, and since we have spectra. So this is, I had a hard time visualizing the radial velocities, but this is basically like a nearest neighbor radial velocity map of the galactic center in old stars. There's nothing particularly interesting in this plot, but what if you look at the young stars? You know, you could kinematically, you immediately see that there's a disk at the galactic center in young stars. So this is the power that by combining kinematics you get. OK, but we're not talking about the young stars today. We're talking about the old stars. So lots of people have talked about the cusp, so I don't need to go on about why it's important. But we wanted to test whether the galactic center had a cusp. Because we see all these old stars. So in principle, we should see a stellar cusp because we have a massive black hole as well. But if you look at the red giants, now this is the bright giants. This is the surface density profile as a function of projected distance. It's super flat, right? Like the density profile is fairly steep here, but then it goes into like a core-like profile at the center. So this has been termed the missing cusp problem because how do you get rid of all these giants compared to Bocal-Wolf? Reiner will talk more about what happens at the fainter end later. This story is complicated, actually. So another thing we've been trying to get at is by adding kinematic information, you can try to get a better measurement of the three-dimensional profile of the cusp, right? Because the thing I showed you previously was just a projection. So if you add the acceleration measurements, accelerations essentially give you a line of sight distance, and that will break the degeneracy from the projection. So we do this using a likelihood analysis by having a part of a likelihood that depends on the acceleration, z, which is the line of sight distance, projected distance, the mass of the black hole. These acceleration depends on mass. And then this component, which does not depend on the acceleration, which is just the projected position of the stars. So you take all the stars that we've measured at the galactic center, select out only the old stars, and then add in acceleration information. This is kind of what you get as the gamma of the slope in three dimensions. So it's still very different than Bacall-Wolf. It's like 0.7, gamma 0.7 or so. But what's interesting is the acceleration we're going to add is only for 12 stars, and it improves the gamma measurement by like over 40%. So accelerations is a powerful way, I think, of getting at the density profile in the very inner region anyway. Okay, but Reiner will talk a lot more about that. I'm going to jump into a slightly different topic, which is metallicities and abundances of the nuclear star cluster. So I've been thinking about the nuclear star cluster for a while, and the way we've separated out the populations, we don't make a distinction based on anything else other than is it a red giant or is it young. But there's a lot of information actually embedded in the spectra. And this information, I think, is what will help us understand how the nuclear star cluster formed. And by that, I mean that there are two main theories about the formation of nuclear star clusters. One, which is the infall of globular clusters slowly builds up this central region. Another is that gas can form, the stars can form in situ, like the young stars today, and then you accumulate mass that way. So one way you may be able to tell whether it comes from clusters far away or formed in the center is if you look at the abundances. So we know globular clusters. We've studied globular for many years. We know the abundance distributions of globular clusters. So we can try to find some of the same signatures. In reverse, if we see signatures that are unusual for compared to the rest of the galaxy, it may indicate something that these stars are formed at the galactic center. Okay. The other important thing about the metallicities is that it helps in terms of your star formation history. So in order to know the star formation history, there is a dependence on metallicity. So these are just 3 isochrones. This is K-band magnitude, and then this is temperature. You can see that if you change the metallicity from 10 times below solar to higher than solar, you get very different inferences about the luminosity and the temperature. Okay, so for a long time, there were not very many measurements of stars actually at the galactic center in terms of metallicity because the region is so crowded. So in about 2015, there are about 10 measurements. So in this plot here is a metallicity distribution. So you should look at this white distribution here. So at the time, everything looked fairly solar. But like I showed you previously, we had tons of spectra. So what happens if you use this spectra now and to try to find the metallicities? So the way, I'm going to talk about the way we did it. There's lots of different ways one can measure metallicities, but the way we did this was fitting a spectral grid. So there's already a grid computed basically by other folks who sampling spectra at different effective temperatures, surface gravity, and metallicity, the parameter we want. So these parameters are all correlated, which is why we need to fit this together. And so we basically use a Bayesian inference with this likelihood. And this is just an example of fitting the sun, which it's easy to do because we know what the sun looks like. But here is here's an example of the fit at the galactic center itself. So you can see that if you do a joint fit, you can get in the posteriors the correlations out. So for example, log G can be correlated with TEF, for example. And we've also tested, we basically tested our grid with other stellar spectral libraries to make sure that our metallicities are accurate. So there is that sets basically our metallicity uncertainty is our comparison to empirical standards. So what do we get at the galactic center? I was pretty surprised, which is that the galactic center contains a huge range in the metallicities of stars. So at the top here is a low metallicity star, so a metallicity of below 10 times the sun. The middle is sort of solar-ish, and then here are supersolar. So this is 0.67. So you can tell, so different ways to tell that it has low metallicities, different than just the fit. For example, there are these really strong iron lines at K-band. You can see that they go, this one basically doesn't, you don't even see it at this metallicity. Okay. And so what does the distribution of metallicities look like at the galactic center? So this is the distribution that we see. About 6% of stars have metallicities below 0.5. And that's minus 0.5 is where basically the most metal-rich globular clusters that we see today live. So
are you comparing with the inner globular clusters or all globular clusters?
All globular clusters. So even the most.
Would be only the inner ones that came in.
So even the most inner one, basically their metallicity is at minus 0.5. So that's why I'm setting this limit here, and that's how I'm defining low metallicity is. That's a good question. It's actually kind of difficult to measure. So when you only have when you have just young stars, you only have basically hydrogen and helium, and so there are no iron lines in the near infrared anyway. So as far as you can tell, it's sort of solar-ish, but that encompasses a lot of things. Yeah, most of the metallicities are actually very high metallicities. So I should warn you that these high metallicities do come with systematic errors, because you can tell in here that our model, which is in blue, doesn't even capture some of these lines. Like there's this line that's like not even present in the model. I'll get to that shortly, but okay. How does our metallicity compare to just the inner bulge? Let's just say. So let's say if you were to make stars in the inner bulge and throw them in, what should they look like? So it's really nice because of apogee now, and apogee actually did survey the inner 2 degrees of the galaxy, and that's what's in blue here. And this is comparison to the nuclear star cluster. So you can see the nuclear star cluster metallicity distribution is significantly shifted. Thanks.
These stars, these are giant. You have accelerations for them, so you know that they're actually at the center?
So there are several lines of reasoning for why we know they're at the galactic center. One is that the stellar density is really, really high compared to outside the cluster. So if you just take a probability of observing a star outside the cluster, maybe about 1 star is not in the cluster. Because we're looking at a very tiny area of the sky, less than 10 arc seconds by 10 arc seconds. And so you're along your line of sight, you know sort of the inner bulge distribution, and you can estimate that way. The other way you can look at the velocity dispersion of your population, and the velocity dispersion is basically the velocity dispersion around a supermassive black hole. This will become important actually quite soon. So that now we have the metallicities. What can we do with them? Right? Like we want to be able to now separate out the populations by metallicity. Does that tell you something about the formation of the nuclear star cluster? In spatial distribution, there doesn't seem to be any difference between the different metallicity populations. So if I took the high metallicity population, which I'm calling this red one, and I look at the density of the low metallicity population, they look very similar. So this is data from Feldmayer, Krauss et al. This is using KMOS now. So this is much wider than the other distributions I'm talking about. So this goes out to like 30 parsecs, so beyond an arc second. Beyond a parsec. So it goes to 30 arc seconds. Okay, so this next part is really preliminary. I only got this result like in the last week or so. Is if you look at the kinematics, there is a slight difference. So if you just split the population in 2, which is at 0.3 metallicities, a metallicity of 0.3, you see that the low metallicity population is slightly higher velocity than the high metallicity population. And if you do a KS test, it's about 3 sigma. So that's just sort of on the verge of significance. So I decided to look, what if you split this into a finer metallicity bin? What do you see? And this is what you get. So if you look at the mean radial velocity now of those different metallicity distributions, you see that at the lowest metallicity population is significantly shifted from the highest metallicity population. So this is very strange, and I'm trying to wrap my brains around this. Their mean velocities are different, but their velocity dispersions are all identical. So if you look at the velocity dispersion of each of these metallicity bins, they are basically consistent with each other. So when I looked at this, I thought, okay, so maybe these are just populations not at the galactic center, right? Like, why? That's why they're shifted. But how does it have a velocity dispersion of 100 kilometers per second and distributed basically around the black hole as well?
How do you measure radial velocity?
With the spectra.
Sure.
Well, like here, right? If you look at radial velocity is one of the parameters.
So how many objects are in your how many lines do you actually cover? Maybe you're not.
You use all of them.
Yeah, but maybe some lines you're not that much as you showed, and then the different rates.
Yeah, so you can look at systematic. So that's if you believe. So if there's a systematics between metallicity and radial velocity, that would be the case. But you see the difference between radial velocities. This is extremely high. Like to be wrong by 100 kilometers per second, it's really bad. Like if we're this far wrong, all of orbits are wrong, basically, right?
How many objects are in your most metal 4 bin?
So in this, there's about 7 objects.
So what's the chance just randomly, if I have a truly perfectly similar thing and I just pick 7 things randomly, that my 7 give a mean that's that different?
Yeah, so that's what the error bar is.
So it's only, that would happen 1 in 6 times then, is that right?
Right, so I think the thing to look at is that it's the differences between the population.
Are you really saying this is more powerful than the KS test?
So the KS test is it's just splitting my population too. I wanted to know, is that because does it look different because one population is really different? Do you know what I mean? Like maybe at a certain metallicity, it's a globular cluster that fell in, so it just shifted the whole distribution. And maybe that's true. Maybe this extremely metal poor guy is it's like an infall of a thing.
But it really is only 7 objects, right? 1 in 6 times you will randomly be that different, if I understood your error bars. If they're just, there's 1 sigma.
Oh, sure, yeah.
Other bins.
Yeah. But the probability of that your high metallicity is this different than your low metallicity, that is a very different distribution.
But your error bar at high metallicity, systematic error bars are quite high, right? So the spread of the right 4 data points, the data you're using for it is quite uncertain.
This? Oh no. So this whole sample has like 700 stars, and this bin alone has like 300 stars.
No, but my point is things contributing to your most metal-rich bin could be in the third from the right bin because your error bars in your metallicity are quite large, as you said yourself.
Oh yeah, so I think one would need to do a more careful statistical analysis about how the errors in your metallicity shifts around. But this is, this is the first time I've seen like a metallicity dependent component in the nuclear star cluster, which is really interesting to me anyway. Am I out of time? Oh, I have 1 minute. Okay, but the thing I wanted to get to is abundances. So because melicities I think are an interesting track, and especially these very high melicity stars, I started taking a high resolution spectra at Keck on these stars, so you can get individual elemental abundances. First of all, I want to just prove that we have a low melicity star. So you just take this, basically, if you look at a globular cluster, essentially, and you just overplot them. This doesn't even have models. You can tell that the spectra are very similar for stars with the same temperature and metallicity. Okay, so that's good. But what about the high metallicity stars? So that's where things get interesting. So these are the metallicities that didn't really fit my model. So I looked at the most high metallicity open cluster in the Milky Way, which is NGC 6791, and it has a metallicity of positive 0.3. So that's what is in orange. And then the galactic center, there's two sources, one in black and one in blue, and you overplot them. So most of the lines are very similar. The galactic center one is slightly more metal rich. I could go into why more, but the most interesting thing, though, are these lines I've marked in red, which at the galactic center is extremely abundant compared to this, this open cluster. So this open cluster's abundance in scandium is about solar. So this means that these elements must be significantly above solar. And so we use a more complicated model now, which is to just run spectral synthesis so that you can change the different elemental abundances. You can see that basically you need a scandium over Fe of at least 1, basically, to fit the stars at the galactic center. So this is an extremely high jump in metallicity. So there are three elements that are anomalous at the galactic center. There's scandium, vanadium, and yttrium. So the big puzzle, though, is these three elements are formed by totally different mechanisms. So scandium is formed in type 2 supernovae, vanadium is formed in type 1 supernovae, and yttrium is formed in AGB winds. So what's going on? Like, why, why is the galactic center so weird? That's kind of like my never-ending question. But so there's something going on that I think is really interesting about the chemistry at the galactic center. What does this imply about the supernova rates at the galactic center and other implications? I haven't really thought through it. I've just gone through the abundance measurements. And I just want to point out that these scandium abundances and metallices are way off from any galactic trend. So this is scandium over Fe as a function of Fe over H in the Milky Way disk. So the most metal-rich components of the Milky Way, essentially. And you can see that as you get to more metal-rich, you should get more normal solar-like scandium. But we're like way up here. These are 2 sigma upper limits, basically, or lower limits, basically. So we're kind of up here. The reason I don't have an exact measurement, unfortunately, because the models don't predict any of this. So I have sort of, it's hard for me to basically say how accurate I am in these abundances. Okay, so I'll just end with the fact that every time we add a new dimension of data at the galactic center, we get surprised, and maybe we learn something new. And I think these metallicities are one way to do it. Thanks.